All right, this is the first lesson in Unit 8. This would be new material for the AP test, or that's not going to be on the AP test, but still good information to have, especially if you're moving forward in any AP calculus or calculus classes next year in college or whatever that looks like. So as we move forward for the next few weeks, this is what we're going to be working on. And as you can see, it says the day one is on the area between two curves. So we all know, just as an example, that the area underneath the curve is found by, if I want to find that area underneath the curve, then I do the integral from a to b of whatever that function is. And that would tell me the area under that curve. So if I want the area in between two curves, let's start by looking at what it is that I want and what it is that I can get. So what I want is I want this area right here. And let's call this red function f of x. I'm going to go and throw that in over here. Let's call this green function g of x. So I want to find the area in between the two curves. So what I'm going to do is I'm going to start by taking the area of all of f of x, and then I'm going to look at the area underneath just g. So if I take all of this pink area and subtract out this green area, that would leave just the blue area. So in this case, what I'm going to have here, this is going to be the integral from a to b of f of x. This is going to be the integral from a to b of g of x. So to get this, I want to take this and subtract this. So to get this area over here, I'm going to go the integral from a to b of f of x minus g of x. That is going to be how you find the area in between two curves. And it's always going to be the top function minus the bottom function. Sometimes, as you'll see in examples, that's going to be pretty obvious which one's the top function, which one's the bottom one. Sometimes you're going to have to do a little work to figure that out. And sometimes within the course of one problem, that is going to change, where the top function is no longer the top function. So we'll look at one of those examples in each case. All right, so first example, it says, find the area of the region bounded by the graphs of x squared plus 2, negative x, and then these two vertical lines, x equals 0 and x equals 1. So first step for me is going to be to draw a picture. All right, so let's start with x squared plus 2. So that's a parabola that has been shifted up 2. So that's going to be this part of the parabola. I'm going to... All right, that's that function. Now I'm going to move on to y equals negative x. That's just a line in the negative x direction. Again, these go in this direction too. And then they say from x equals 0 and x equals 1. So x equals 0, I'll draw these in a different color, is that vertical line. And x equals 1 is that vertical line. So the region enclosed by these four lines is this region right here. That's a 1, that's a 0. So as you can see, we have a top function, we have a bottom function, and we are going from 0 to 1. So to find the area in between those curves, I'm going to go from 0 to 1 of the top function, so x squared plus 2, minus the bottom function, which is negative x, and just simply solve that integral, and that will give me my area. So in this case, 0 to 1, I'm going to rewrite this, x squared plus x plus 2. Now I'm just going to take the integral. The integral of x squared is x to the third over 3. Integral of x is x squared over 2. Integral of 2 is 2x. I'm going to evaluate that at 1 and at 0. So let's evaluate at 1 first. I get 1/3 plus 1/2 plus 2. And I subtract when I evaluate at 0. Well, that is 0 plus 0 plus 0. A lot of zeros. All right, and then when I add all of those up, I'm going to use a calculator really quick. 1/3 plus 1/2 plus 2 gives me 17/6. So 17/6, or approximately 2.83. That is the area of this shaded region. So it's always top minus bottom. All right, let's take a look at another example. Example 2, this time they give us the two graphs, but they don't give us the endpoints. So what that means is that that's going to be our first job, is to figure out what those endpoints are. So first thing I'm going to do is I'm going to go again graph. Let's see, negative x squared plus 2. So up 2, and then it's a negative x squared. And then my second graph is just y equals x. So I can see on my graph where they cross. I don't know exactly where those are, so I'm going to need to do a little bit of algebra before I can solve my integral. So what I'm going to need to do is I'm going to need to set these two functions equal to each other and then see where they meet up, see where they intersect. So I'm going to add this stuff to the other side. I'm going to add x squared. I'm going to subtract 2. So I'm going to get 0 equals x squared plus x minus 2. That's going to factor to be x plus 2, x minus 1. So x is negative 2 or positive 1. So that would be my negative 2. That would be my positive 1. So now I can see where my endpoints are. So that was step 1. Well, I'll call step 1 graphing it. I'll call step 2 solving for their endpoints. And now step 3 is going to be finding the area. And the area is going to go from negative 2 to 1. The top function is this quadratic, so negative x squared plus 2, minus the bottom function, which is just x. All right, I'm going to simplify. I screwed that up. This should be negative x squared plus 2. Okay, so I'm going to simplify this up a little bit. I'm going to say negative x squared minus x plus 2. I'm going to take the derivative now. Negative x to the third over 3 minus x squared over 2 plus 2x evaluated from negative 2 to 1. Be careful when you're plugging things in with your positives and negatives. So when I plug in a 1, I get negative 1/3 minus 1/2 plus 2 minus. When I plug in a negative 2, I get negative 8/3 minus 4/2 minus 4. And when I combine all of that together, I'll use my calculator again really quick. Negative 1/3 minus 1/2 plus 2. And I distribute that minus, so that's going to be a plus 8/3. That is going to be a plus 2, and then a plus 4. Which is going to give me a total of 9.83. I think I screwed that up. I'm going to look really quick back at my distribution. Actually, when I plug in a negative 2, I think I made a mistake here. When I plug in a negative 2, that is actually going to be a plus 8/3. Negative 2 to the third is negative 8, and then the second negative makes it positive 8/3. All right, so let me try that again. Negative 1/3 minus 1/2 plus 2 minus 8/3 this time plus 2 plus 4 gives me 4.5. So there is my area that is in between those two curves. Again, top minus bottom. Okay, let's try example 3. It says find the area of one of the regions bounded by the sine and the cosine curves. So step 1 is to graph. I will graph the sine function. Then I will graph the cosine, which starts at the top. So what they want is this area. And as you can see, if we just continue this on, those would be the same. There's a level of symmetry there. So they're all going to be the same. We just need to find one of them. So again, first step is to figure out where these intersect. Where does the sine equal the cosine? And if you remember back from your trig, that's going to be pi over 4 and 5 pi over 4. So that's going to be my endpoints. So let's start up the area function, pi over 4 to 5 pi over 4, top minus bottom. So in this case, the top is sine, the bottom is cosine. Let's go ahead and do the integral. The integral of sine is negative cosine, and the integral of negative cosine is negative sine. And I'm going to evaluate that from 5 pi over 4 to pi over 4. So let's plug in some values and let's see if we can get an answer. So when I plug in a 5 pi over 4 into cosine, I get negative root 2 over 2. So the opposite of negative root 2 over 2 is root 2 over 2. When I plug in 5 pi over 4 into sine, I get the same value. So I'm going to get a minus, a negative, or a plus root 2 over 2. Minus. All right, in this case, when I plug in a pi over 4, I get root 2 over 2. So negative root 2 over 2 minus, and again, when I plug it into sine, I get root 2 over 2. So I have, when I distribute this, it makes that one positive and that one positive. So I end up with 4 of these root 2 over 2's, which is 2 root 2. So the area of each of those intersections is 2 root 2. All right, final example. The area bounded by these regions. Okay, so again, I'm going to need to graph these. So in this case, we're probably going to want to use the help of something like a Desmos. So I'm going to go ahead and plug those into Desmos and then graph them as we go. I don't know if we have the ability to graph these out. Maybe we do. But either way, we'll use Desmos for now. Negative x squared plus 2x. That is a parabola that goes through at 0 and at 2. And then 3x cubed minus x squared minus 10x also goes through at 0 and 2, and then also over here. I'm going to graph them both on the same graph so I can see where they intersect. Sorry that you guys can't see this. I'm going to redraw this. All right, so first graph. That's going to be your cubic, and then your quadratic. It's going to look like that. All right, so once again, probably should have had that figured out beforehand, but either way, now that we have our graphs, you can see that there are two different regions that are bounded by this graph. So what we need to do is we need to figure out all three places where these intersect. So we already know two of them. We already know this one intersects at 2, this one intersects at 0. This guy we're not sure of. And the other thing to notice is that in this section on the left, the green function is on top, and in the function on the right, the pink graph is on top. So we're going to need to figure out two different areas. So I'm going to call this guy area 1, I'm going to call that guy area 2. So what we're going to need to do is do those separately. So first thing, like I said, step 1 is to figure out where they intersect. So I need to know, where does negative x squared plus 2x equal 3x cubed minus x squared minus 10x. So I'm going to move some things over. I'm going to add an x squared. I'm going to subtract a 2x. So I'm going to add an x squared, and I'm going to subtract a 2x. I'm going to end up with 0 equals 3x cubed. Those cancel out, and I get minus 12x. I'm going to factor out a 3x, which is going to leave me with x squared minus 4, which is going to be 3x times x plus 2 times x minus 2. So you can see this guy gives me an x at 0, a negative 2, and a positive 2. I already knew the 2 and the 0, so that guy is a negative 2. So to figure out the total area, I'm going to start by figuring out area of 1 and adding in area of 2. So area of 1 is going to be the integral from negative 2 to 0 of the top function, which is the green function, so 3x cubed minus x squared minus 10x. Then I'm going to subtract the top function, or the bottom function, negative x squared plus 2x. This is area 1. And so when I do that, I still get negative 2 to 0, 3x cubed, negative x squared plus x squared gives me 0, negative 10x minus 2x gives me minus 12x. Alright, so when I take the integral, I get 3x to the 4th over 4 minus 12x squared over 2 from negative 2 to 0. When I plug in a 0, I get 0 minus, let's see what happens when I plug in a negative 2. I get 16, 4, 12 minus, let's see, 6 times 2 squared, 6 times 4 is 24. So I get 12 minus 24 is negative 12, and then the opposite of that is 12. So that's the area of 1. Area of region 2 would be from 0 to 2. This time the top function is negative x squared plus 2x minus the cubic. Alright, so it's still 0 to 2. I'm going to simplify. I'm going to end up with negative 3x cubed. I still get a negative x squared and a plus x squared. And then I end up with a plus 12x. So it's the exact same integral, just opposite signs. So I get negative 3x to the 4th over 4 plus 12x squared over 2 from 0 to 2. Plug in a 2. and I get essentially the same thing. I get negative 12 plus 24, which gives me 12. So the total area, which we said was area 1 plus area 2, is going to be 12 plus 12, or 24. So there is your area of that problem. Again, hardest problem of the set, because we have to, number one, do the steps where we figure out where they intersect, and then we also have to do two separate integrals for the two separate areas of the function where the functions change. All right, so work on the homework, check your results there, and